What's up, friends? Sorry that this is coming a day late for our first section of the class, and then it's not on the slides. For our other sections of the class, it will be on this first slide. I'm going to send this to you personally. Don't worry about it. Today, we're going to learn about color. Here's a little do now. So this is on the week 3, day 2 slides that's in the Google Classroom. I'm going to check this do now to see if you've done it, so make sure you do it. I've got 4 questions here. I want you to pause and do those right now. Okay, explanation coming now. So if you haven't done it, pause and do it. So is this atom in the ground state or the excited state? Remember, the ground state is when the electron is as close as possible to the nucleus. It's in the first orbital. So because this is not in the ground state, or sorry, it's not in the first orbital, it's in the second orbital, it must mean it's an excited state. How can you move this electron to increase its energy level? Well, if the ground state, the orbital that's closest, has the lowest energy level, that means as we go up, we get more energy. So how can we move this electron to increase its energy level? Ooh, we hit it to this outside orbital. In order to make that electron move, it has to absorb some kind of energy to go up in energy. Sometimes that's heat, sometimes electricity, sometimes that's a photon coming in, hitting the electron and making it come up. How could you do the opposite now? Decrease its energy level. So if it's right here, it can go down to the first orbital. This has a higher energy than this one, so it needs to move down. When it moves down, it no longer takes in an electron, or sorry, it no longer takes in a photon. Remember, a photon is a particle of light. No longer absorbs light. It now releases light. During that process, it releases light. That explains number 4. It goes down an orbital, it releases a photon, releases light. So last class, we learned about these bioluminescent creatures that are really cool. I think they're really cool. My screen's probably like in the way of them right now. We learned about these vocab words like ground state that we just saw, right? Excited state, where the electron's no longer in the first orbital, and photons, the little squiggly boys, the light that gets shot out. And there's a really important statement. Orbitals have different energy levels. This class, we're going to learn why do orbitals have different energy levels. So it starts in the first black one, then there's a higher energy in the second one and a high energy in the third one. Where like 3 is the highest, this is the middle, this is lowest. These colors, by the way, none of these colors here like really ultimately mean anything. I just like color coded it to make it easy to see. But what does actually have something to do with colors are the squiggly lines, are the photons. These actually do relate to color. Okay, so today we are going to zoom into the orbitals. So if you see like, think about this as like orbitals right here. This, although it's not curved, it's flat, is the same thing as this. So see how this like electron's the closest one to the nucleus? It's at the bottom, it's at the ground state, just like a ground is below you and on the floor. This is at the ground, on the floor. The electron's in the ground state right now. This is an excited state, this is an excited state. These are both higher energy than the one that it's in right here. Okay, so this, you should pause this and read this to yourself 2 times. Pause this, read this out loud to yourself 2 times. This is so important to this learning goal. If you know the order that this happens and you can be confident in why these things happen, you will pass this learning goal. So pause this, read it to yourself twice. Okay, I'm going to read it now. Electron is in the ground state orbital. Energy is about to enter the atom. This is how light is made from any atom. So we start at this state. We start at the ground state. Atoms absorb the energy and the electron moves to an excited state. The atom emits a photon and the electron returns back down to the ground state. So we're going to use this for the next slide. So put these in the correct order. We've got different pictures here. We got an A picture, a B picture, and a C picture. At the bottom, you're going to say first comes either like ABC, then comes ABC, and finally comes A, B, or C. Each one only gets used once, and you're going to use the words and you're going to connect them to the pictures that you see. So pause, do that. So our correct answers, we start in the ground state over here. Look, the electron's in the lowest possible state. And energy that we see up here, energy is about to come into the atom. Then the electron goes up to the excited state. That's what's happening in B. So second comes B, goes up into the excited state. And finally, it goes from the excited state and drops back down It shoots out a photon. It shoots out a light particle. This is where the light that we see, if we see something glowing, it's because atoms are shooting out photons. It's because electrons are moving from the excited state to the ground state. That is when photons are created. So think to yourself, a cycle. Well, why did Murray put this big red arrow here? How come step 4 goes back to step 1? Think about that for a second. Pause, take 30 seconds. Well, the reason I put that here is like, let's think about this. An atom emits a photon and the electron returns to the ground state. The electron is in the ground state. We have now started back where we've now finished where we've started. The electron's back where it needs to be to start the process all over again. Here's an analogy that you're going to pause and you're going to, in this box, I want to see like 3 or 4 sentences. 3 or 4 sentences. How are these diving boards that you see on your screen related to what we just learned? I need to see the words orbitals, energy levels, and photons. So we've got a bunch of diving boards here, and you're creating an analogy. Like, how is what we just learned about light creation related to diving boards? Pause. I want to see a couple sentences. I'm going to be checking that, so make sure you do it. So here's my explanation. So the water, you can't, if you're on a diving board, you can like jump off the diving boards into the water, right? But the water's at the lowest possible energy. I can't jump off of anything. Just like if all of these were orbitals, like I could jump down. So I could say the one that's at the highest, like that's gonna have the most force, the most impact when I hit the water. It's the highest energy. And then it goes second, third, fourth, and fifth. At the water is the lowest energy level. You can't go any lower than that. It is ground state. It's like at the ground. This might be like water, but we're gonna think of it as like the ground. This isn't a perfect analogy because you can't really imagine jumping from the highest energy to the second highest. Like I can't imagine jumping off this platform and landing on this one. That's like concrete to concrete. They're not next to each other. That's gonna break my legs. That's gonna hurt. So you could think, why are higher orbitals higher energy? Why are these higher dives more exciting? Well, think about this. Like this is like, a diving board close to the water. That's kind of exciting. Or think about this dive that is like really high off the water. Like that's really exciting. You can like do all sorts of crazy flips like in all the space that you have. It's really exciting. There's a lot of force. That's a lot of energy. By the way, Chinese divers, this is one of the Chinese divers, the Chinese national team. They're so insanely good. The reason that this looks so perfect is because they are extremely good at this sport. And no, you can't go any lower in the ground state. Look at this guy. He's trying to jump from the ground state somewhere lower. You can't. You can't go into the nucleus. The ground state orbital is the lowest you can possibly go for an electron. All right, here's a name that diver exercise. Who's this pseudo-famous diver? Look at that. Look at that form. Look at that. Look at that mediocre form. I'm pretty proud of this. You might have guessed this is me in college, back with a whole lot less hair on my head. I dove in college. I also swam in college. It was something that I was super passionate about. I also had a ton of fun. This is like me training over the summer, in between years, trying to get good. I thought I ended up pretty okay for somebody who dove very infrequently. This is not my main sport. My main sport was swimming. Cool. So, this is a triple Lindy. This is like a YouTube video you can watch in your own time. It's like funny, it's fun. Open up the slides and check it out. It's a very famous scene from an old movie. Okay, pause this. And well, before you pause, what do you see here? What do you think? And what do you wonder? So, what is an observation? What do you think is this is explaining? And what do you wonder? What's a question you have? I want to see all three on your slides. So how do we think that these two pictures relate? Again, pause. How do these two pictures relate to one another? You see this on the left, you see this on the right. Okay, here's the big time explanation here. Different color photons have different energy gaps. Look at this. Number one, purple has a big energy gap. Blue has a smaller energy gap. Green has a smaller energy gap. Red has the lowest. So you might say like, it looks like a trend. It looks like a pattern. Photons on the red side of the spectrum over here have less energy than photons on the blue side of the spectrum over here. Blue and purple, high energy photons. That's why if you look at blue light or purple light, it's going to hurt your eyes more than if you look at red light or orange light. And that's just a fact, folks. That's just a fact. Um, and this is blue side of the spectrum. Like I know purple is like the highest energy, but for some reason in chemistry and physics, people say like blue side and red side. Remember if you learned in earth science about red shift and blue shift, it's like being on one side of the color spectrum and the other side of the color spectrum. Um, Number three, white is the mixture of all photons. Black is the absence of photons. So if you see white light, like I have in my room right now, it's a mixture of all the photons coming out. That means it's shooting out blue photons, yellow photons, red photons, orange photons, green photons, and they all rain down on the stuff around me, and then stuff reflects back the certain color photons. Like this thing is pink because it's reflecting from that white light, hits this pink pen, and then this pink pen shoots back pink photons into my eyes. So I'm like, ah, this is pink. This pen doesn't create any photons. It's just bouncing the photons off of the white light, which is creating photons, and now I get to see it. That's why the thing is like, have you ever heard of the phrase a black light? A black light's not really a black light. A black light is an ultraviolet light. It's like, it's purplish, and it goes like beyond the purple to where we can't see it. Black, and now in like if I look at my wrist brace, this is like the absence of photons, meaning that it reflects no photons. So I look at it, I'm like, I see the absence of photons here. That is like that's the brain's perception of it. Okay. So we've got three things on this slide now. One, two, three. Use those three to describe the phenomena you see here. Pause. Take a second. Okay, so we've got different elements right here. Lithium, strontium, sodium, copper, potassium. Remember that the periodic table that we saw briefly organized all of these elements by their little symbols. So like instead of writing out the whole word lithium, you just wrote Li. Instead of writing the whole word strontium or Sr. Sodium comes from a different language. It might be sodium, So. Comes from a different language. That's why it's Na. You know, some languages aren't the same in Espanol as they are in English. So like we say, ooh, even though they might sound similar sometimes they're like totally different words. Like rain and lluvia, like not the same thing, right? Cool. Um, cool. Yeah. So the explanation here is that the lithium, when it's emitting photons, emits lower energy photons than potassium. It's on the red side. Let's go back over here. It's on the red side over here, low energy, versus, say, sodium in the middle, orange, which has higher energy than red. Ooh, then green, which is over here, higher energy. We can see also like, ooh, green's higher energy than red. And this is like a bluish purple, kind of hard to tell. Ooh, bluish purple, highest energy over here. Potassium releases the highest energy photons. So that's going to be it for this part of the video. But folks, you need to open up this video here. This is explaining the assessment for today. It's the final assessment for 1.3. Please watch this. Final assessment. I will remind you that you can use all these slides that you see here in order to complete the assessment, but no copy and pasting. I need to see the final assessment in your own words, or else I'll return it to you and say, hey, in your own words, please. That's it. Deuces. Peace out.